All right, we're back. We are game 2005 in the fall 2017 semester, and it's week 8, part 3 of our broadcast. We're still talking about Newton's laws. We have a little bit more to cover for this part. And I want to go over some other examples. So this one here, I was talking about it before the last, before we left, the last video that I was talking about. Neat. We can talk about what the free body diagram looks like. You can see that there's two, right? You've got one free body diagram that represents this side, and we've got another free body diagram that represents this side. But guess what? If they're not moving, we know that they're in equilibrium if it's not moving up and down. If it's actually moving, like we know that it's moving in one direction, like if you're given a problem that says, okay, and the right arm is moving down at this many meters per second or something like that, then you know the system is not in equilibrium, right? And if it's not in equilibrium, then you can account for the acceleration in a particular direction, okay? Now in this case, you're given the same for both objects. The tension is the same for both objects. Where you have two masses, one and the other, you have a pulley, right, as an example. But even though the gravity, the mass on the left has less, it's a smaller mass, it looks like, than the one on the right. And you can see that one is actually physically lower than the other one, right? And you can see that the way they've drawn the diagram, it looks like mass 1 is actually lighter because the magnitude of the vectors are different than mass 2. But actually, in this particular case, we don't have information of that nature at all. In fact, what you should assume is that gravity on mass 1 and mass 2 is equal, right? Because we don't have, no one said that mass 1 is 10 kilograms and mass 2 is 20 kilograms, and somehow they're in equilibrium. We don't know that. Right? We know nothing. We know that there's two masses, and we know that they're linked somehow. We also know that there's gravity going down on the left mass and gravity going down on the right mass, right? And somehow the tensions, right, between the two of them are keeping both objects in equilibrium. That's what we know, right? So it's a different kind of problem, and they do have they talk about how to solve the problem. Same thing goes with this other option here, where you have an incline, right? I'm just talking about different kinds of problems here. You have an incline in this particular case. See if I can zoom in here, right? This is a different kind of zoom that we did last time. So we have an incline, but in this case, you have a mass. Oh, that was weird. No, that's not what we wanted. We wanted to go way up here. 41. Down here, pretty close to this one, yeah. We have a mass that is coming down an incline over here, and we have another mass, as an example, that's being accelerated up. So the acceleration is moving up this way because this mass is coming down an incline. Now, again, without any other information, we don't know anything about this system, but this is the way you would set it up, right? Where you have two free body diagrams, one that looks like this, one on the right. So for people who are watching, this one would be one free body diagram for this mass, right? Or sorry, for this mass. This one would relate to A, right? And this free body diagram would relate to B, to this one, to this scenario, right? And then what you have is a resultant force because one system affects the other one. Now, am I ever going to get that complicated with you? No, right? But you could figure out one system from the other. Why? Because it depends on what information you're given. If you're given this information that the object on the left, right, is moving up at a specific acceleration, right, or velocity, then you could find out that obviously the object on the right, chances are is heavier, more massive than the object on the left because it's going down an inclined plane and pulling the other object up. You know this, right? And you can see that from the way the diagram A is drawn, that you have an arrow going up, which means there's an positive acceleration, which means it's countermanding the negative acceleration due to gravity. It's greater than that, right? Because it's moving up, right? And that means that this on mass 2 must be big enough to pull mass 1, right, and to countermand its the effect of gravity on mass 1. Okay. So there's two systems here, and you combine them, and you figure out if the systems were separate, what would have. So for example, let's put some numbers here. Mass 1 is 10 kilograms, right? what's the, again, going back to, we use 10 a lot just for for test cases. So the force of gravity on this object, mass 1, would be approximately 100 newtons, 98 newtons actually, negative, right? And then let's say, for example, mass 2 was something like 20 kilograms, right? That makes sense, 20 kilograms. So it's going down, some kind of incline. Well, what you would do is you'd use this free body diagram to calculate the force across the incline. And the way you do that is you have to figure out what the angle theta is, right? Whatever that angle is that's incline. Let's say, for example, it was an incline of 10 degrees, pretty big incline in real life, right, at 15 degrees. Then you take 10 degrees, that would be your, and you take the mass times gravity, mass 2 times gravity 2, right, to find the x component, and mass 2 times gravity 2 with cos theta to find the other component until you find the total, the net forces m2g, which is this middle one right here, right, across this object, right? So notice that this object here has another component going this way, up this way, right? And this would be the tension, the wire that's resisting, right? Because there's a resistance because of the other mass, right? If it's still traveling in that direction, and if the pulley represented zero resistance, there's no resistance, I would transfer the energy here, right? Where I have 100 newtons going this way, right? If it's still moving down this way, right? I have 100 newtons going this way, and I have a mass of 20 kilograms pulling down this way. Am I moving? That's the question, right? And of course, after you figure things out, we can figure this out together. We can figure out that maybe we do have motion. What do you guys think? Did you figure it out? Think about this, right? If I have 100 newtons going this way, right? Because that's what it would be, right? And if it's 10 kilograms, the other mass is 10 kilograms. This is 20 kilograms, right? Now I'm using a different mass. I'm 20 kilograms times the force of gravity. Let's say it's 10 for our purposes in our head, right? So 20 times 10 is 200 sine theta, right? And if my angle is, let's suppose, 15 degrees, and again, I'm just going to pull up my calculator here. So if I say that, maybe I should put up the other kind of calculator, the scientific one. So if I say that 15 degrees, right? So sine of 15 is 0.25, right? As an example, multiply that by 200, right? Which is roughly 51 newtons of force, right? Going across this plane right here, 51 newtons of force, right? But there's 100 newtons of force going this way. So right now, this component alone is not enough to tell us that we're moving in any direction, right? But what about this one? Well, we take the mass again, 20, right? So 200 cos theta. So again, so 51 newtons of force. Let's keep that in our heads for a second. Oops. So say 15 cos theta, right? Multiplied by 200, right? So 193. So we have 193 this way and 51 this way. So we take those two things, we use Pythagorean Theorem, we find the total force. This force is greater than this force. We have motion in this direction, down the plane, down the incline, right? It's pretty simple. And how do we figure that out? Let's just use these numbers roughly, 193 and 51, right? So we say 193 times 193, okay, times 193, right, is equal to 37,249, right? And 51 times 51, let's see if I can do this properly, if I can remember. 37,249. Yeah, I know, I'm just doing it this way, right? Plus 37,249, right? 39,000 approximately 850, right? And if you went to get the square root of that, it's roughly 199 newtons, right? Guess what? It's almost 200 newtons. Remember I said saying 200? It's almost 200 newtons going this way. 20 kilograms, 10 kilograms is 100 newtons going this way, right? And 200 newtons going this way. Guess what's going to happen? It's going to go down this way with a force of 100 newtons. Okay, so if I have a force of 100 newtons And if I know that my mass, right? If I know that my mass is 20 kilograms, what's my acceleration? It's the other way around. Force is equal to mass times acceleration, right? So if force is 200 approximately, so 199.62, whatever it is, let's say 200 to make it even, right? 200 is equal to my mass of 20, right? And I don't know what my acceleration is. So I take 200 divided by 20, which is 10 meters per second, approximately, right? Which is the force of gravity at the end of the day going down this way, which is what you would have got at the end of the day, right? Because this is twice as heavy as the other one. And we're using an angle of 15 degrees. If we use a different angle, you'd have a different result. Okay, that's how you figure it out. Would I give you problems like this on a test? That's not undoable. That's not like it's completely, you can't understand it, right? But I probably want to keep it simple and do the basics first. Like one of these first, just an incline. Because again, we're not going to have a lot of time. Okay, let's get back. So again, this is just, it's almost like we have two problems and we're breaking them, we're calculating, we're trying to figure out both problems to figure out the final result. We're using the results from both problems to figure out the big problem, which is, you know, we're making two free body diagrams for this one. All right. When it comes to friction, right, we use mu, right? Some people call it mu, but it's not mu, it's mu. Greeks call it mu, right? Which is representing the coefficient of friction, right? And what we want to do is we usually multiply, it's a multiplier, right? So what we want to try and do is figure out, depending on the type of surface that you're using, we can figure out the coefficient of friction. Now, typically what I would do instead of this is say something like this. With a friction of 10 newtons. That's pretty good friction, right? With a friction of 3 newtons, or whatever it would be. If I said there's a body with a total friction of 3 newtons, I've already calculated the coefficient for you. You don't have to figure that out, right? It's almost like giving you another force, right? But if you had to, you could calculate the coefficient of friction based on different scenarios, okay? So here's a scenario where you have static friction, right? Where it's keeping a body stable. Remember, an object at rest tends to stay at rest unless you're using some unstable force, right? Well, notice in this particular scenario, I have a garbage can, and I have the force of friction, and we use S to signify friction, by the way. See if I can zoom in here. So friction is S, force of friction, right? Let me see if I can go over here. Here it is. So the force of friction, right? And what you also have is, actually, am I right? FK. Force of friction is that way, but you have a force that's pulling the garbage can. This diagram on the right, right? You also have the normal force that's pushing up, and gravity pulling down. Okay, so you have a mass. So because the normal force and the force of gravity are equivalent, they're cancel each other out. All you really care is the amount of force that you're applying to the object, right? Minus the resultant friction. And friction, you take the coefficient of friction multiplied by the mass, and you get the total force. And that's what's going to slow you down in terms of pulling across a particular object. That's static friction, friction that stays the same all the time. Think about it like a static variable. It's constant, right? Well, maybe that's not the exact, that's not really a great analogy, but I think you guys get what I mean. Okay, so that's kind of the situation where friction, I'm only going to give you friction as a force, but you could calculate different frictions. And I think down inside this this PowerPoint, I also have some typical coefficients of friction. Okay. So again, as long as the object is not moving, then the force of friction is equal to the force. If we're not moving, because I'm pulling it this way, but we're not moving. If the force decreases, sort of the force of friction. If the force increases, sort of the force of friction, because I'm applying the force multiplied by my coefficient of friction to get the resultant force. Basically, I'm calculating the resistance. That's what I'm doing. I'm calculating the resistance that I'm getting across the ground, right? All right. And I'm not going to go into this too much because we're not going to, again, I don't care about you calculating kinetic friction or anything like that. All I care about you calculating is if I add friction to a system that you know that it's going to slow the system down, right? So example, the force of friction of air resistance, right? The force of friction in water, right? I'm going to give you that if I'm going to move you inside water or something like that, or across water. I'm not going to make you calculate. So it's here, to explore it, but I'm not going to really do it with you here. And it actually gives you the coefficients of friction if you really want to know. These are common coefficients of friction in terms of, steel on steel. What's the coefficient of friction? You can see that the biggest one is rubber on concrete. Try and move something rubber on concrete, you're not going to move that thing. It's huge. The amount of force that it takes to move that thing is almost equivalent to the amount of force that's holding it down in general. It's going to be like a huge amount of force. And it's almost impossible to move it. The bigger the coefficient of friction is, the more chances that it's going to resist you, right? So as you can see, ice on ice, there's like 0.1. The coefficient of friction is 0.1, which means almost zero. You can assume it's zero, right? But still not zero. Even ice is not zero because if you take something, a piece of ice and you throw it on some kind of skating rink, I mean, given time, it's going to slow down. If the skating rink was an unlimited, size, the volume was unlimited because there's still a slight amount of friction, ice on ice, right? But if it was like some kind of truly 100% frictionless surface, a perfectly frictionless surface, then this would be zero, right?
Always wax.
That I don't know. That makes no sense to me, right?
Zero friction.
Yeah, it's crazy, right? We should just wax the wood when we drag the sled, right? Sled, that's what they did. They took wax and put it on the bottom of the sled, on the sleigh, and they would drag it across snow, and then it'd be like, there's no friction. Push it, right? I don't think that's true. I think it's probably negligible. That's what I think it is, right? There's still going to be some friction. So that's kind of a neat idea, the idea of friction. I want you to understand that there is friction, but I don't want you necessarily to calculate it. I'm just going to give it to you. And most times you can figure it out. Like if you actually looked online and in a real life scenario, you just take the coefficient of friction, you take it and plug it in. There's actually a friction calculator online. Take it, calculate it, and you have the total newtons. And then you can use that to inject into your system to give you a true to life simulation. And again, you can use the sum of all friction that you're applying to a force. For example, you might have more than one type of friction that's being applied. Why? Imagine if you have a surface with the surface friction, as well as some kind of kinetic friction because of, let's say, air resistance, right? So you have friction due to air, you have some kind of surface friction, maybe there's two surfaces, you're sliding something inside of an object, and one side is greased and the other side isn't, right? As an example, then you have two different frictions, one on the top of the object, one on the bottom of the object, and if you're moving it fast enough, you might even have air resistance. A good example of this might be an elevator that's broken. Right? You have a broken elevator, it's fit inside of a shaft, right? And maybe one corner of the elevator, for whatever reason, it's rubbing against the steel. So you have steel and steel friction plus zero friction everywhere else. How does that misbalance the system? And you can figure it out. Not for us, it's not for our scenario, because it's a very complicated scenario that I'm talking about, but that's where that would come into play. So here's the example of this incline that I was talking about, the extended incline example, where we have not just the incline of an object, with some angle theta, but also the friction that's opposing the object moving down. Okay, and I think when we combine all those things, we would get the the total friction as a friction force moving against the slide of the object moving down. So back to our other scenario, if I have a 20 kilogram object, right, that is on an incline of 15 degrees. As an example, let's use the same thing. And we're moving at about 100 newtons of force that's being applied to the object, right? If I have a frictional force of 10 newtons, that means my resultant force moving down the incline is 90 newtons. And if you take that 90 newtons over the mass of an object, which is 20 kilograms, you can figure out the acceleration is going to be less than 10 meters per second, right? Because once you move the equation around, force equals to mass times acceleration, you can figure out that it's going to be less. And the way to do that, of course, is to plug in the numbers. So we just kind of did that in the last example. So if, again, if we use the same numbers, 20 times gravity, right? So again, assuming that gravity is 10, nice. Assuming that gravity is 10 meters per second squared, not 9.8 for a second, just for this scenario, to make it easier for us to calculate in our heads, times the mass, which is 20 kilograms, times sine theta, which would give you something like 51 or 53 newtons. I think that's what it was, because sine of 15 degrees, right? And then once you figure it out that the this part here, this vector down here would be approximately 199 newtons minus the force of friction, which would be, let's say, 189 newtons. And then you could figure out what it's going to be. Now, we don't have what we had before in the pulley example, where we actually had 100 newtons taking, kind of removing. We didn't remove 100 newtons. We're only removing 10 newtons. So it'd be like 180 newtons or something like that of force. And if you took that 180 newtons, let's calculate this now. Sure what I'm talking about. So I've took 180 newtons of force, approximately. I'm just making this up here. And you want to find the acceleration due to gravity, or the acceleration, the total acceleration. We know that the mass is 20. Divide this by 20. And we know that the total net acceleration is 9 meters per second in the downward direction towards the incline. Okay, a negative 9 meters per second, right? Which is pretty cool. That means that we know that's how fast it's moving down the incline, using force is equal to mass times acceleration. There's another way to do it, though. We could also figure out that when we talk about momentum in the future, in a future lecture, you're going to see there's another way to calculate the total acceleration based on how a system is balanced, and that energy is neither created nor destroyed, right? So we're just transferring energy. We have a kinetic potential here, and we're going to talk about potential energy later on. But think about this: it's almost like we have a latent energy built into everything we have. Anything that has mass has a built-in energy. Okay, and an example of this would be before I go to the lecture for momentum, which is going to come down in a couple weeks. But let's suppose that I'm holding a mass of 10 kilograms in my hand, off the ground. The idea is that the potential I could drop it is high, right? Because I have it in my hand, off the ground, right? If I had it on a desk, it'd be a different story, right? As long as it's off the ground, though, it has some of this, almost like this inherent energy that's built into it. And depending on how high off the ground it is, it has more energy. Why? Because if I have an object that's, let's say, for example, let's suppose that I'm 2 meters high. I'm not. Well, let's suppose that I'm 2 meters high, right? And if I have an object that's worth 10 kilograms, weighs 10 kilograms, and I take it 2 meters off the ground, right? If I drop that object, right, it's going to have an energy it's going to accumulate speed as it comes down to the ground, right? Whatever that is. The resultant kinetic energy that's going to come down is something that we have, where we're going to call potential energy in the future. So an object always has some kind of potential energy, right? And if I let it go, it's going to convert the potential energy into kinetic energy. Motion. Kinetic energy is all about motion. And we're going to talk about that in the future lecture. So we can use that, a system of momentum, as opposed to this idea of force equals mass times acceleration. Although one can be derived from the other one. So don't worry about it now, but I want you to keep it in mind that the reason why it's moving is because it has, if you think about every object as having energy stored inside of it, right? If we all have energy stored inside of ourselves, right? Because if you think about it, going back to Einstein's theories, right? Mass is energy in a different form, a solid form, right? If mass is energy in a solid form, right? The same thing with chemistry will tell you the same thing, right? Then therefore we're storing energy inside of ourselves. We all just some kind of form of energy, right? And if that's true, if we're some form of energy, then the higher off the ground we are, the more potential kinetic energy we have. Okay. And let's move on. So that's kind of a typical scenario. Here's another one. I'm going to have some kind of an object on a frictionless surface. Now we know, we just saw that the coefficient of friction, there's no frictionless surface. But let's assume that something on ice is 0.1 or almost frictionless. We assume frictionless surface, and if I move an object, right? You can see that the coefficient of friction is right here, right? Fk, that's pulling us back, right? And if I slide, if the motion is to the right and the coefficient of friction is to the left, then for parallel surfaces, it's really, you're just going to subtract one from the other, right? So you can say, oh, however much I'm going to put this way, I'm going to subtract from this way to get the total acceleration. That's what I'm doing. That's what I'm going to try and figure out, okay? So it's not that difficult to figure out. And once we put it on an incline, right, that's where we get additional forces being applied because of the incline. Okay, again, same kind of idea. There's other scenarios. We're not going to talk about this one. This is if you're using friction across a system with multiple objects, multiple masses. So in this particular case, I have a mass that's on a pulley, and I have some kind of frictional surface. Notice that the surface has little ridges on it. I don't know if you can see that, right? So when you draw the free body diagram, one of the things that I could totally ask you to do is pick the free body diagram and a test that makes the most sense. So here's the system. Which free body diagram is right? This one, this one, this one, or this one? Which one? Right? And that would be a valid question on a test, because I can't get you to draw a free body diagram, but I can get you to pick one. And one of them is going to be right. One of the ones you see. Okay? There's also going to be one that's very wrong. And I'll make sure there's always one that's like just psychedelic. Right? If you see a free body diagram that's psychedelic, you know that's not the one. Don't pick that one. Right? But anyways, if you notice this on the left, these little ridges, sometimes we draw it this way because to indicate that there is friction. This is not a surface that's frictionless, right? And then you see that there's a pulley. Here's a pulley here with a mass. So there's two masses in this scenario. With an angled force, I'm pulling this way with an angle from, that's not flat or straight across the surface. Whenever I pull up at an angle, I'm not as efficient as if I pull across, right? If I pull up, then part of my energy that I need to pull across the x-axis is gone. It's being absorbed into the y-axis. I want you to think about that. It's almost like I'm transferring energy wherever that arrow points. So if I have my arrow that's pointing up, right, there's less energy pointing across, which means that some of my energy is being transferred to the y direction, right? In this particular case, my pull, if a man was pulling this box, right, across a surface, a friction surface, right, it'd be less efficient than if I pulled it across the surface, not up the surface, right? So the lower down your, your center of mass, the low closer to the center of mass, or the zero angle, the better for when we pull things across, right? And that's true too. If you ever try and pull a heavy box in the garage or something like that, right? If you try and pull it from the top, it's not going to move. But if you lower yourself down and pull it down, it's going to move. Because you're lowering your center of gravity, you're actually increasing your efficiency by moving the angle that you're lifting down, right? You're sliding it across. Or if you're pushing it down, it's easier to push across the box than sometimes before. Now, in this case, you're having an opposed mass. You have two systems, right? One free body diagram and another free body diagram. And one system will affect the other one, okay? Here, notice that you have, depending on the angle that you're going to keep into account, some component of force across the x-axis. You're going to calculate that, as well as some component of force across the y-axis, right, this way, right, as well as the normal force, as well as the force of gravity going down. So you have resultant forces, or some force sums across each of the components. Notice that there's also the force of friction you have to take into account here, plus the tension along the cable, which is the resultant force of this system, the second system. When I get you to do something like this, chances are not, it can be complex and it takes time to calculate. Would I do it on an assignment? That's fair game, because now you have time. You can go away, check it out, and come back. Again, for the assignment, like I mentioned earlier today, I'm probably going to cut it down. Instead of like I gave you 4 questions last time, I'm probably going to give you 3. Just to make it a little easier, a little quicker, because you got lots of other stuff going on. Yeah. 3. Yeah, not 1. That was pretty good. They almost convinced me there, but yeah. 1. I'll see what I can do. Maybe I'll cut it down to 2. I don't know. All right. So that's really the most that I want to calculate. I want to go over one more example before I let you guys go. Again, I told you about I'm going to keep it very simple today. It's your first day back, right? So I'm kind of easing you guys in, right? So let's suppose we have this one last problem. Let's do this one last problem together, okay? Now here's we have some numbers, and I want to work it out with you. I have the answers on the other slides, but I want to, and when I have access to Blackboard, I'll definitely put them up for you. And this comes pretty much right out of your textbook. But I want to try and calculate this together. Okay, so now, a hockey puck having a mass of 0.3 kilograms slides on the frictionless, we know it's not frictionless, a frictionless horizontal surface of an ice rink. Okay, why? Because what's a hockey puck made of? Some kind of rubberized or some rubber-like product, right? A lot more plastic now than anything else, right? So you got some kind of plastic on ice. So it's not going to be frictionless. It's going to be close, but not frictionless, right? Two hockey sticks strike the puck simultaneously. Okay, this is interesting, right? Exerting the forces on the puck shown in figure 5.4, the one on the right, right? The force F1 has a magnitude of 5 newtons. You've already been given a magnitude and is directed at a theta angle of 20 degrees, right? That's F1. That's this force down here, right? Okay, and the force F2, which is the force going up, has a magnitude of 8 newtons and its direction of phi. That little symbol that's in the middle, that's a Greek symbol phi. Typically, we kind of talk about it like that, right? So one is theta, the one that has the line across, and phi is the one that has the one going up and down, right? Or phi, some people call it phi, right? Phi, phi, I like to call it phi full fun, right? Phi. And phi is equal to 60 degrees above the x-axis. So this is where this thing here. So this is 60 degrees above the x-axis, right? Determine both the magnitude and the direction of the puck's acceleration. So what was the first thing that you do? First thing, before you anything else. You've got the numbers, but you want to do the first thing. When you're figuring this out for an assignment, what's the first thing you should do? Yes?
Draw a diagram.
Draw a diagram. That's it. Once you can conceptualize, you can figure it out. You can break it down. So how would I draw this diagram, right? Now, where's the gravity? No gravity. Because the normal and the gravity cancel each other out. Do we really care about it? Answer is no. Right? We don't care about that right now because both the force of gravity and the normal force that pushes up from the ice rink is 0. Right? We can zero it out. So all we care about is the resultant force. So imagine if there's a stick that hits the puck that makes it go this way, and another stick that makes gives force to the puck this way. Obviously, it's going to be somewhere in the middle. That's what you're going to get, right? You're going to get some forces in the middle. But the challenge is we have the total forces. We have 5 newtons, right, for F1, and 5, or I believe, is it 5? Yeah, it's 5 newtons for F1 and 8 newtons for F2. We have the resultant force, right? But we don't have the components. We need to find the components. And why is that? Because we need to add up the components to get the middle, right? To understand what's happening in the middle, right? So we also have angles. So if we find a kind of components, how would I find the x component for F1? I would take the total force for F1, which would be 5 newtons, cos theta, cos of 20 degrees, and give me the x component across for the F1 stick. So let's try this out. So if I was to write this down, let's try it out and see if we're right. So I'm going to insert a little object. Let's see if I can insert a text object. And it's kind of hard for me to see, but here it is, text box. Here's my text box. I'm going to say something like this. Well, we know that after we draw the diagram, we know that F1, right, cos theta, right, cos of, let's insert a formula, an equation, right, and we'll insert a symbol. Where's the symbol? I love the symbols. It's probably on the left-hand side over here. Yes. F1 cos theta. Let's say F1. Actually, I could have highlighted this whole thing and done that, right? So if I actually made this into a formula, right? So if I inserted a formula, I could have done that. But this is F1 cos theta. So F1, we know that F1 is 5, right? Cos of 20 degrees. That's what we're talking about here. But notice that also, and we have to be very, very careful when we talk about this. The 20 degrees is south. 20 degrees is like, it's at an angle this way, right? So that's something to think about this. So we have to think about the sign of cos theta for a second, right? But let's try and calculate this. If I look at cos theta, I'm just trying to outline this for you guys in your head, right? So I'm kind of, first thing I would do is draw a diagram. We didn't do that, but let's just do this now. I'm going to go into cos theta, cos of 20 degrees. So I say 20, and if we're right, I say cos 0.93, right, multiplied by 5. So we're going to get a value of some 4.698, let's say. So that's what this will be. So the x-axis, so the F1x is equal to something like we said, 4.698 newtons. Let's just suppose, right, if I'm right, okay? Maybe I'm wrong. And now we also know that along the y-axis, we also have a y component for this force, right? So I'm going to kind of copy and paste this thing. And we've kind of done this before, right, with our we did 1D and 2D motion. This is kind of a refresher about that because that's what we did, right? So the F1 across the y-axis now, right, again would be 5 sine theta. And again, if I go back here, and if instead of cos, I say, 20 degrees, right, is 0.34 times 5, right? It's roughly 1.71 or exactly 1.71. So 1.71 newtons. Okay, 1.71. There we go. I wrote those two values down. But that's just for the F components for F1, right? We also need the components for F2. So we can do the same thing. So let's take these components here, move them over to the side, copy them, paste them over here. Nice job, Tom. Okay, I can't move them together. Maybe again. Here we go. F2, I'll be okay. F2, x and y. Now for the x value of F2, going around this axis here, is F2 is 8 newtons, right? And we know that the angle is 60 degrees, so it's, again, it would be 8 times cos of 60. So let's go find what cos of 60 is. Is that what it is? Yeah. So 60 cos 0.5 times 8 is equal to 4 newtons approximately. Here we go. 4 newtons. Now again, we didn't talk about sine yet, okay? We didn't talk about sine. And now, would x have any other sign other than positive in this scenario? No, because it's moving the motion, if you notice, is moving toward the right. Both motions are moving towards the right of the y-axis, right? So we know some x is going to be positive, right? Okay, cool. So we know that, and now let's go do the other one. So on the y-axis, though, this is where we're going to have a problem. This is where we're going to have this one being negative because we know it's moving down across the y-axis, right? And this one is positive, right? Because it's moving up across the y-axis, right? So if we look at what y is, again, it's 8 times sine of theta. So if I go sine of theta, so sine of 60, so 60. And if I go sine, that's 0.86, and multiply that by 8, right? Which is roughly, or exactly 6.928, let's say, 6.928. 6.928 newtons. Okay, cool, right? So how do we figure this out? If we just use regular logic, we just add these together, right? So we'd say that the resultant force then, right, across, let's say that the resultant force, let's say we just call it F. We'll see if I can grab these two things, as well as those two things, and move them over. And let's just grab these two things and copy and paste, move that over. So the resultant force on the x-axis, so that's results. We'll call this FR, lowercase r. Resultant force along the x-axis, if you add these things together, would be approximately, let's say, 8.7, right? 8.7 newtons, if we're right, right? And if this is true, we take this minus 1.71 and add it to 6.928. Let's just figure that out. So I'm not going to figure that out by hand because I'm just not going to do that. So I'm going to say 6.928 minus 1.71 is equal to 5.218. So 5.218 newtons, right? got both those two forces. Now, we want to find the resultant. Well, those are components, right? And we want to find the total force. We know that we're going to move up and into that direction. And the way to do that, to find the total force that's across the, that angle. Now, we know the forces, right? But we don't know the angle. We don't know the angle yet, right? Because if you notice, it says, what's this thing asking for? The force F2 has a magnitude of 8. The direction of phi is equal to 60. Determine both the magnitude and the direction of the puck's acceleration. Okay. Well, we have components, right? We have the components, and now we need to find the magnitude. Well, the magnitude is easy, right? We just take x squared, plus y squared is equal to z squared kind of idea, or a squared plus b squared is equal to c squared, which is the Pythagorean theorem, right? So to find the total result, so let's just go take all this aside again. Right? We're going to calculate this final result here for the magnitude, which we'll call Fm, the magnitude of the force, the resultant force. Let's copy this one over here. We'll call this the magnitude of the resultant force, FRM, let's say. And what is that? Well, 8.7 times 8.7, maybe someone can calculate that for me. 8.7 squared plus 5.218 squared, and take the square root of all that. And that would be the thing. So we're using the Pythagorean theorem to figure that out, right? Wait, can I use the Pythagorean theorem? Can I? Here's the thing. If we have two forces, right? We're x and y. Because we're working in squares, we can't, right? Even though these two angles don't add up to 90 degrees, they add up to 80, right? We know that this is not a right angle triangle, but it doesn't matter. We're finding the angle in between, right, by adding the two forces together. All we're doing is doing vector addition at the end of the day, right? That's what we did here. When we did this, F1x plus F2x is equal to FRX. That's just vector addition. We're adding two components of the vectors to get the final resultant vector, right? And that's what we're getting. We know we can find out we can draw the vector now because we know that it's across the x-axis, 8.7 units across the x-axis, and 5.218 units across the y-axis, going in an upwardly direction because there's more upward force than downward force. 8 newtons this way, and only 5 newtons this way with a different angle, angled much closer to the upward angle compared to the way down, right? So we know that's the case. So how do we calculate this? We can still use Pythagorean theorem because we're just taking the resultant x and y, and whenever we have a frame, an x and y frame, we can totally calculate that. That's just calculating the magnitude. So what is it? Anyone calculate that for me?
10.143.
10. Okay, I'll take your word for it. So that would be the total magnitude, 10.143. Now, does that make sense? I'm taking two forces. I'm taking 5 newtons, and I'm taking 8 newtons. And instead of getting 13 newtons, I'm getting slightly less. Why? Because both forces, some forces along the y-axis are in conflict. I'm losing energy along the y-axis. How much energy am I losing? Approximately 1.71 newtons of force, which makes sense. Instead of getting 13, I'm getting something like 10 point something. That's where the loss is, right here. This is where the loss of energy is, right? Along the y-axis, where I normally would have, if they were both shooting along the x-axis, and there was no y component whatsoever, we'd just be adding the forces together. But this is the magnitude. Okay, cool. So I've got the magnitude. Okay, I don't know the direction. How do I find the direction from the magnitude? Well, if we think about it coming from the origin, right? If this is the 0, 0 mark, right? And if I want to find the angle, right? How do I find the angle? I have, remember, it's all trigonometry again, right? I want to find the angle. I have my sine over cosine, right? I have sine over cosine or tangent. If I take the inverse tangent, right, using the magnitude, right, then I should be able to get theta, what theta is, right? So what's the tangent? Well, if I take sine over cosine, which is 5.218 newtons, right, that's the total force, over 8.7, right, and I use the inverse tangent of that, or the arc tangent, right, then I should be able to get the thing. So can someone do that? Can someone take 5.218 divided by 8.7, right?
It's like 31 degrees, basically.
Give me the exact number. right?
30.96.
Is it? You figured that out? So what did you do? You took the when we did this, remember, in trigonometry way back in the first couple lessons, right? We took the y, we divide it by the x, we get a ratio. That ratio, that 0 point whatever it is, we take the inverse tangent of that to get the angle, and that's how we would do it theoretically. Am I right? Let's see. What did you say? You calculated that?
Like 30.96
degrees.
Yeah.
Positive.
Yeah.
Right? Because it's here. It's in this frame, right? If it was down here in this quadrant, it would be negative. A negative angle, right? Some negative value. But we know it's positive because there's more in the positive. There's more, everything's angled more towards this way than it is this way. If this was 40 and this was 40, it might go right across the x-axis. You would know that. It's pretty simple to figure out, right? Just depending on the forces, right? Well, because there's more over here, right, then it's roughly 40. If you think about it, if it was equal forces, if it was 8 newtons going down and 8 newtons going across, right, and if this was these are the angles we were given, we know it would be 40 degrees, right? 8 newtons, they cancel out, 40 degrees, exactly. Not quite 40 degrees because there's some down here and there's more up here, right? So it'd be something else. Let's try and figure this out. Or, sorry, not 40 degrees, it'd be 0. 40 and 40, 0. The other way around is what I'm thinking. So how do we figure this out? If I was to put down your angle, you said some angle, some theta, we'll say angle is equal to 30 degrees, something like that, 30.1. What is it?
30.96.
30.96 is what you figure out degrees, right? Okay, let's see if we're right. Let's see if we figure this out right or if we're completely way off. Did they figure it out differently? Well, let's see what they did. They said first we conceptualize, we started the figure, we draw it, we figure out that F1x plus F2x is equal to F1 cos theta plus F2 cos theta. Hey, we did that right, right? That's exactly what we did. We did the same thing. We do the same thing for the y. The sum of the x and the sum of the y's is what we did, right? Now, they did the sum of the y slightly different because when you look at it on top here, the sum of the y's, let me see if I can bring it in. Because they added them all together, right? Here we go. So here's the sum of the y's. So we take F1 sine theta plus F2 sine theta, and we get the sum of the y's. Right now, here's an interesting fact. They didn't subtract in this particular case. Did I make a mistake or did they make a mistake? Right? Because on the y-axis, we're not going in the same angle. So this is kind of weird, right, that they did that. They could have done it like this. They could have taken the value, and instead of taking 20 degrees, they could have converted it as well. That's another way. You could have taken along the whole axis and say, okay, at an angle of 340 degrees, right, which is the same as an angle of 20 degrees on the lower, right? We got the same kind of angle, right? But they more or less did what we did. What they got is the acceleration. They used force equal to ma instead of doing the other way around. They used Newton's laws to figure it out, right? And we didn't use 0.3 kilograms. We didn't even come near to using that, right? Because it would kind of equal, kind of even itself out at the end of the day, right? Because we said, hey, we assume that, and I kind of led you down that way. I said we can assume that the normal force, right, and the gravitational force, we can assume that they cancel each other out. That's what I said, right? In this case, they didn't do that. What they did was they said, oh, no, we're going to divide it by 0.3 kilograms to find the answer, right? And they got a certain acceleration across the x-axis and a certain acceleration across the y-axis, right? Just a different way of figuring it out. At the end of the day, it's the same answer, right? They just did it using force equal to ma, and we did it, right, using the inverse tan too. Look at this inverse tan, right? And we did it based on the on forces. Now, they calculated acceleration, and we used forces, newtons the whole way through. Could I figure out acceleration when I have newtons? Yes, because I have the mass. The mass is 0.3 kilograms, and I have newtons, and I can figure out the acceleration in a particular direction. So I didn't interpret it properly when I read it, but at the end of the day, we got the same answer, right? Which is basically a ratio of y over x, right? Because once we have our components across the y-axis and our components across the x-axis, we have the right component, we put it in the inverse tangent function, and bam, we have the approximate angle. So we did it right. We didn't use F equals equal to ma, we used trigonometry. Pure trigonometry with forces. You can do it both ways. To me, at the end of the day, I mean, if I ask you to use Newton's laws, if I say using Newton's second law, then you're not supposed to use trigonometry. If I say specifically don't use trig for this one, use Newton's second law, then you do this, right? Which is almost the same. We still broke down the component forces. They used see, they did use negative sign here, negative 20 degrees, right? I just put the negative symbol across the things I knew was negative. At the end of the day, we did the exact same one. Okay. Questions for this one? So here again, this is a classic problem. That's why I kind of showed it to you. We did it a different way, but at the end of the day, we can figure out two forces by creating a component where actually what we're taking is the components, both the components of f2x and f2y, and f1x and f1y, and creating the getting the resultant angle, right? And the resultant total force. If the resultant total force, if we go with what is said here, right? And just to see what this says here, it says the magnitude and direction of the puck's acceleration. This is what we missed, right? Acceleration, not newtons. Force in newtons. If it says the total force in newtons, then we did it right. But we actually did it wrong. We were supposed to calculate the acceleration, which you could have done after. Because we know the magnitude, right? Because the magnitude of the force, which is kind of, I think, a better way of doing it myself. I would have done it this way, which is kind of what we did, is 10.143. If you take that, right, and divide it by the kilograms, which is 0.3, let's see if we're going to get the same result, which we should. So we're just moving the equation around now. So we're saying 10.143 newtons, right, divided by 0.3, which is roughly equal to 33.81 meters per second. That doesn't make any sense. What did they do differently than we did? That's really fast. Oh no, it's pretty close. 33 point. That's whack. That's out of whack. That's like crazy puck. That's a puck going at an insane speed. Meters per second. That's a huge amount of. So that's a crazy speed here, right? But we're right actually. 33.81, roughly 34. Right. So that's pretty right. Right. So that's how we figured it out. You just take you use force equals to ma. If they said what's the acceleration, I probably would ask you like this. Give me the net force. Give me the net acceleration. Give me the angle. Sorry, I would have probably broken out like that for you in an assignment. But classic problem again, and I think it's something that we can you can expect to see on an assignment, not on a test. A test would be much simpler. All right, because on a test, then I'd probably break it down a little easier, or I might give you more information. Okay. Okay, any questions around today? So today is all around Newton's laws. We covered three laws of motion, right? What's law 1? Right, an object at rest tends to stay at rest, right? And let's just go back to that slide. Let me go back to 100% here so I don't drive myself and you crazy, right? Which is, where did I put it? It's here somewhere. Oh, yeah, so an object at rest tends to stay at rest unless some other force applied. Second law, which is key, force equal to ma. That's the second law of motion. These are total questions I could ask you on a test. What are the 3 laws of motion? This, and this. Or what's the second? I might ask you, what's the second law of motion? You should know F is equal to ma, right? The third law of motion, which is for every action, is equal and opposite reaction. We didn't really have a chance to get there, but really what we're talking about is if I push something with a certain force, I'm going to get some kind of result, some kind of force reflected back on me, right? An example of this would be the whole cue ball, or an example, a pool ball, right? Where some of that force is going to be reflected back, right? Especially if the pool balls are the exact same mass, right? So they're going to move, yeah. We're actually transferring energy from the stick to the pool ball to the other ball, right? Minus the friction of the table, because the pool table is not frictionless, but because it's a sphere that we're sending down on the table, it almost acts like a frictionless surface because the sphere itself is made to roll, right? It's not being slowed down like if it was a cube. If we had a pool table with cubes instead of spheres, they would be different. It would be a different kind of game, right? Because there would be the force of friction along the pool table would actually slow the cubes down more, right? But the spheres would actually, there's almost zero force there, right? It would actually go. Now, there's still some force of friction on a pool table, because if the pool table was an unlimited size, again, it would slow down eventually and stop because of the furry pool table, right? It's not like ice, and even ice would slow down. But so when it hits another pool ball, the thing is there's energy being transferred to the same type of mass from, let's say, the cue ball to the white ball to the other balls, whatever it is, right? There's energy reflecting back. And so there's energy loss. When I'm transferring energy from one pool ball to the other, I get some energy back because of this pool ball that's sitting there with an amount of mass, a rigid body, basically that's reflecting energy back to me, right? Now, it's not going to be the entire amount of energy, but some energy is going to be reflected back, which means you're going to have a loss of energy in the system, right? Because I'm shooting some energy this way, I'm getting some of it reflected back to me, which I'm going to slow myself down, because I'm going to go to a different angle, right? That's what's going to happen here. And that's what the third law is all about, which is more of a complicated thing than you think. When you first look at it, you're like, ah, it's easy to do. And we're going to handle the third law more in momentum and all that centripetal force and all that kind of stuff more than anything else. Questions around Newton's laws or anything else we talked today? Because this is the main thing. If you guys don't get Newton's laws, like I said, it's a failure, right? For me, not for you. Because it's like kind of a basic case. It's almost like Newtonian physics is the simplest physics to understand because it's very straightforward. Okay, that's it for me, guys. We're going to end off a little early today. Expect that next week we're going to have a full lecture and lab, right? Again, we're talking about a slightly more complicated case next week, and also expect that next week you will receive your assignment number 2, right? Where I will pare it down. Like I said, I'll probably only have something like 3 questions. There won't be any programming involved. You can work with a partner or 2, like last time, right? Each of you can handle 1 question. You guys do the assignment on your own, so it prepares you for the test. And then when you get your test, you've worked with the formulas enough that you understand how it works, okay? Most of it's going to be on this today's, next week's, and the following week's lecture to do your, so expect those are the chapters I'm going to cover from the book on the assignment, okay, and on the test. Questions? Guys, thank you so much. See you next week.